X was
0.
it was at 0, 1. Oh, so it was the point 0, 1 and
Negative 2, 5.
negative 2, 5. So we built in our table here 0, 1.
Yeah.
Do you remember what we do is we look at our value, we put our value for X for one of our stationary points.
Yeah.
We look a little bit left, a little bit right, and stick these values into dydx. Why do we look at dydx? What does that tell us about?
Gradient.
The gradient. Okay. Just you know find it easier to go there. Because if I'm always in your way. If you pull it. So we look at the gradient, we found that this was a negative value, didn't we? Yeah, and then we found we know when it's 0, it's 0, and this was a positive gradient, so it was a minimum point. So we're going to do the same thing now with negative 2, 5. So negative 2 goes here, we know that that gradient is 0. A little bit to the left of that would be negative 3, and here, negative 1. Well, handily, we've already worked out when x is negative 1. We know that that's a negative value. When x is...
Should we put the value?
You can if you want. I can't remember what it was.
Negative 3.
Negative 3. When x is negative 3, what's the value? Do we know? And then put it in. After 26, positive. Okay, it's going to be positive because we know it's going to go up, 0 and negative, so that tells us it's a maximum point. We get the idea of it? Yeah? So we're never actually too worried what the actual value is. We just want to know, is it positive or negative? So is it uphill sloping or downhill sloping? Well, they've asked us to now sketch the function having done that. So how does that help us? Well, we've got our axes here. We know our two stationary points are at negative 2, 5. So negative 2, 5 is one of our stationary points. Oh gosh, I can't see my thingies at all. I'm going to pretend that's where they are. And I know that the other one is at 0, 1. So that's at 0, 1. So if I look back at the original function, what kind of graph is it? It's a cubic. So do we remember that they do this or this? Vaguely? So cubic graphs either go up, or down, up, down. So that tells me that if I've got one stationary point up here and one down here, we knew that this one here was the maximum, so that it has to go like that. And we knew that this one was the minimum, so it has to do that. And then it must swoop up. So obviously it is on the calc paper. What you can also do is chuck it into your calculator. So you can put the actual original function into your calculator. And you can find where the two maximum and minimums are by doing all your calculations. And then you can see from a sketch that this one is negative 2, this one's 0. So this one had to be the maximum value because we knew it to that. Does that make sense as well? So this is further left, so it had to be the maximum. This is towards the right, so that one has to be the minimum. Alright, so that's looking at gradients. Our other option, as I said, is looking at the second derivative test. So the second derivative rule is that if your second derivative is less than 0, so in other words, if it's a negative value, then the point is going to be a maximum one. If the second derivative is greater than 0, so if it's positive, then the point is going to be a minimum. Now, I always think it's the wrong way round, right? I always think that if this is negative, that sounds like it should be the smallest, so it should be the minimum. But you need to try and get it into your head that it's the opposite way around. So if this is negative, it's a maximum point. If it's positive, it's a minimum. Now, if the second derivative is equal to 0, it's going to probably be a point of inflection, but you just need to investigate further. So points of collection have no stationary values. You need to consider concavity. So we'll talk about that later. Just FYI, concavity is my least favoured area of this topic. I think it starts to get a little bit crazy and can confuse lots of people. So it could be a situation where I say to you, do you want to hear about it? And then those that don't want to. It could be, it's like a concavity question might have 1 mark allocated to it, if you know what I mean, it's the end of the question. So it could be something you're like, you know what, I don't really care, that's not confusing. But if you are, then I can do it in small class later. Anyway, so, e.g., find the importance of stationary points on the curve, blah, blah, and determine their nature. So, the first part is going to be just the same as it was last lesson. So, to find stationary points, what do we know? Or what do we have to do? Say again?
X equals 0.
X does equal 0. Yes, we need to find the derivative. Good. So, in this case, we would write f dash x. So let's find the derivative expression first. Cameron, can you help me out? Lovely. So that's my expression for my derivative. Why is that helping us find stationary points? What information do we know?
Let's take away 15.
Yes, it's going to take.
I'll find us with 3.
That talks about the gradient. Good. And what do we know about the gradient of stationary points?
0.
It's 0. So to find the stationary points, we find the derivative and then put that equal to 0. Is it all kind of typing that?
Right, so when do we find the second derivative?
In a second.
So,
this could be on the non-cap paper, so we're going to practice our factorising. I can see that 3 is kind of fit everything. So yeah.
What did you just think?
So I put out a factor of 3 for everything.
But what did you just put 0 in the place of x?
No, because you have to remember that the gradient is 0. Yes? The value of x isn't 0 necessarily. It might be, but the value of the gradient is 0. Okay? So I factorise, because remember that's what people always forget to do when they get a number here, they forget about factorising. And then we know that we can factorise this baby. And we're looking for 2 numbers that multiply to give -5. And those same 2 numbers have to add to give -4.
It's like just 2 and 2.
5 and 5. Oh my goodness.
Negative 5 and 1.
That's the same thing. Negative 5 and 1. So we've got our fact. We factorised it. So that means our 2 values of x are 5 and -1. Transient. Alright, so we found our 2 x values. Do they really have the 3? So the 3 has no significance because we have to remind ourselves, why do we factorise? Well, we make it equal to 0 and we factorise because that means now I've got 3 things multiplying together. For that product to equal 0, one of those things has to be 0. That's the only way of getting an answer of 0 when you multiply stuff. This one obviously cannot equal 0, so it can't be that one. Were you aware of that's why we always did this? No, because I'm with you right now when you're talking. Alright, so the reason that we always make sure that quadratics are equal to 0 so that we can factorise them, and then we've got things being multiplied together. So that means that either this one is equal to 0, which meant that that was x was 5, or this bracket was equal to 0, which meant that it was -1. This is never going to equal 0, but it needs to stay in our working. We can't just forget about it. Because this is actually our derivative, not getting rid of it. Okay, so we'll go with that. Now, they actually want us to find the stationary points, so we have to find the y values. Okay, so we're now going to find f5. Remember our fancy way of showing the substituting 5 into it. So this is going to be 5 cubed, subtract 6 lots of 5 squared. Oh, this is a lot of work, isn't it? Because they want to know the stationary points. We know they happen when x is 5 and when x is -1, but we want to know the actual y coordinate. Sometimes they just say when do they occur, and so we can stop there. But they've actually said what are the stationary points, so we have to find the y is. And I don't know what that number is. Does anyone know what that number is?
125 minus 150.
Oh.
25.
I thought you were actually telling me.
No, man. 150 times 5.
-101.
I'm guessing.
Now, see?
Oh, wait, no, it's not.
Well, secretly.
This will be similar to me.
So we've got -1 cubed. Why did I have to put my -1 cubed in a bracket?
Because that's the top.
Because it's negative. Thank God. Yeah. So we've got -6, -1 squared, minus 15 lots of -1 plus 1. Okay. Alright, so we know that our stationary points are 5, -99, and -1, 9. Okay, so they are our two stationary values. Stationary
Oh, we
points.
just found y?
Yes.
I was a little.
So we found where they are, but we need to now find their nature. So this is where the second derivative comes in. So we're going to now find the second derivative. So f double dash x. Do you remember that's how we showed the second derivative? And that's differentiating this expression here. So, Shelter, can you differentiate that backwards, please? This one here.
6x.
Yep.
Take away 12.
Nice. Okay, so we say 6x minus 12. Yes? And now what we're going to do is we're going to find the value of that second derivative. I reckon you're going to fit it on the bit paper there, FYI. So we're going to find the value of that second derivative at these 2 points. Okay? So when x is 5, f double dash 5 would be 6 lots of 5 subtract 12. What's 30 subtract 12?
17.
Nearly.
28. I didn't even think about it this way.
He constantly secondhand. She said you're close to Jennifer, and then you come out with
I know,
something.
I was already constantly
Okay.
She constantly said she had, but she said it.
And now we're doing 6 lots of -1, take away 12. What's 6 lots of -1?
Negative 72.
And then take away 12.
Negative
18.
Negative
Okay. So we found that when x was 5, we got a positive value for the second derivative. Yes? So when x was 5, we got a positive value, which means it is a minimum point. Right? So when it was 18, when x was 5, it was a minimum point, and when x was -1, it was a maximum. So this point here was our minimum point, this point here was our maximum.
So you do the second derivative. That's all I did.
Yeah.
Why did you
Alright, so we've differentiated. We now know that our derivative is equal to 0 for stationary points. Now, whenever we are solving equations like this, we try and factorize first. Is there anything that is common to these terms? 2x is common, yes? Awesome. So we're left with
2x squared minus 3x equals 1.
okay, so we have 2x at the front. We've then got 2x squared minus 3x plus 1.
2 and 1.
This is one of those more complicated quadratics to factorize. That's where we have to multiply these terms. And you remember that?
But here,
We did this in like
2 and 1.
Yep. Maybe you're naive.
I've never done this.
I don't remember.
Oh, okay. Oh, do you know what? Okay, I need to stop it. Stop it.